And gentlemen, that handsome young man in the top left there is Brian Leakey, and he put out a video earlier today demanding that I pay him 10 grand because he thinks he's the first person to get a position fix using a flat Earth map.
All right, Roohif. For starters, I never claimed to be the first to achieve this, and also I want to let you know I wasn't trying to be demanding. Apologize if it came across like that, but I feel like I did exactly what you challenged me to do. So that's what I intend to prove objectively in this video.
So Brian published a video a few days ago with his solution. Now these GPs are entirely made up, but that's fine. He's just demonstrating the method. And his method was to use a website called ns6t.net that allows you to create an AE map centered on the GP of each star, and each map has a given radius which corresponds to the circle of equal altitude. And when he combines all three of these maps, you'll see that they share a common point around Quito, Ecuador, and that was the position fix in Brian's hypothetical. But the big question is, did Brian use the globe? And to answer that, you actually need to understand what we're really asking you to do when we say draw three circles of equal altitude on a map. Because what we're really asking is, what are the coordinates for all the points that make up this circle? So, for example, and these again are completely made up numbers, we've got the GP of the star at 42 north, 121 west, and we want to know what are the coordinates of the point that is, for example, 1500 nautical miles away at an azimuth of 37 degrees. Or, more fully, what are the coordinates for all the points that are 1500 nautical miles away in every direction? But just for this example, we're going to find the coordinates of one point at an azimuth of 37 degrees. And that means we need to do some geometry, yay! So this is the AE map, and what I've done is rotate it such that it's aligned on the longitude of the GP, which was 121 west. The latitude of the GP is 42 degrees north, so assuming a 60 nautical miles per degree scale, then the GP is 2,880 nautical miles from the North Pole. And then we draw a line that is 1,500 nautical miles long at an azimuth of 37 degrees. And what we want to find are the coordinates for the point at the end of that red line. So how do we do that? Well, we can actually make a triangle here, and since we've got two sides and the angle between them, we can solve this triangle using the law of cosines to get the length of the third side. And that length, of course, is the distance from the North Pole. So here's the law of cosines, and if we plug in all the values, we end up with a distance for that third side of 1,909 nautical miles. And if we use the rule of 60 nautical miles per degree, we can work out the latitude of our mystery point to be 58.18 degrees north. But what about its longitude? Right, so now we use the law of sines to work out that angle between the green line and the third side. And that works out to be 28.22 degrees, which is the change in longitude from the GP. So subtract that from the longitude of the GP, and we get 92.78 degrees for the longitude of our mystery point on the circle of equal altitude. So just to recap, we've got the GP of the star, and we want to know the coordinates of all the points that are 1,500 nautical miles away. But for this example, we've just chosen an azimuth at random, 37 degrees, and the coordinates of that point work out to be 58.18 degrees north, 92.78 degrees west.
All right, Roohif. For starters, man, you're using the law of cosines, and that's not how the AE map works. Okay, that's your method. That's not my method. That's a straw man method.
But what if we use the globe map? Well, in that case, we'll be using the Haversine formula. Now, I'm not going to waste anyone's time deriving the Haversine formula. If you're really interested, you can just Google it. So all I've done here is write some very quick Python code, plug in the GP of 42 north, 121 west, and I ask what the coordinates are of the point that is 1,500 nautical miles away at an azimuth of 37 degrees. And you'll see that it spits out a position of 59 degrees north, 91.43 degrees west. So a little different to what we got from the AE calculation, and it's about 65 nautical miles away from the position.
Okay, if you're trying to use law of cosine to map the celestial hemisphere projected down on a plane, no wonder you think it's impossible on a flat Earth. This is a total straw man. This is not my method. And why are you going to the North Pole? And I'll entertain it for a minute, and we'll see how this math works from the surface of a sphere. I don't think you're going to like it, though. So we're going to use the same numbers, 42 north, 121 west. We'll start there, we'll put a point, and then we'll go up to the North Pole like you did. Let's see how this works on the surface of a sphere. And then we'll run down to 93 west and 58 and change north. And then we'll go back where we started. Let's see what your azimuth looks like. You say it only works on a sphere and doesn't work on the AE map. Let's see what our output is. That's your output right there. You claim that works, but AE map doesn't? That's ridiculous, man. And now you're about to use your same method and apply it to what I showed. This is your method, not mine.
Okay, so now we know how to work out these coordinates. Let's apply that to Brian's azimuthal projections that he used in his video. So for his first projection, he chose a GP of 40.1 south, 78.3 degrees west, and the radius of that circle of equal altitude was 4,450 kilometers. So here's that map, and what we're going to do is choose a point on this map with a known latitude and longitude, and then see if we can figure out what formula it's using. And I've chosen a point where lines of latitude and longitude cross, just to make it easier. And that point that I've chosen is 50 degrees south, 40 degrees west, which is just northwest of South Georgia Island. Right, so as before, the map is centered on 40.1 south, 78.3 west, and the radius of the map is 4,450 kilometers. Now, using the dimensions of these green and purple lines, I can work out that the azimuth of the point is 123.25 degrees, and by scaling the lengths, I can work out that this map is telling me that the point is 3,163 kilometers from the GP. You're quite welcome to do your own pixel counting if you don't believe me, but remember the question we're trying to answer is, on what map do you arrive at 50 degrees south, 40 degrees west, if you start at the GP and travel 3,163 kilometers at that azimuth? So let's check the AE map first. So again, here's our triangle starting at the North Pole. We can work out the length of the green side by using the 60 nautical miles per degree of latitude, and it comes out to 7,806 nautical miles, or 14,457 kilometers. So again, we can use the law of cosines to solve for the third side, and it comes out to 16,406 kilometers, or 8,859 nautical miles. And again, if we divide that by 60 nautical miles to get the degrees of latitude from the North Pole, that comes out to 57.65 degrees south latitude. And that's already not looking good for the AE map, because we were expecting a latitude of only 50 degrees south. But let's get the longitude anyway. So just like we did before, we apply the law of sines to work out the change in longitude from the GP, and that works out to be 9.28 degrees. So the longitude of our point turns out to be 69.02 degrees west. So using the AE map, the point that is 3,163 kilometers away from the GP of the star at an azimuth of 123.25 is 57.65 degrees south, 69.02 degrees west. That is not what we were expecting. We were expecting 50 degrees south, 40 degrees west. This is not using the AE map.
Roohif, it's egocentric. Why in the world are you measuring the North Pole from way down there? And besides that, why the hell are you measuring distances inside of the circle of equal altitude? Are you trying to tell me that that circle of equal altitude ain't equidistant all the way around? That's what you challenged me, bud, and that's what I gave you. And again, why in the world are you running lines all the way up to the North Pole in this coordinate system, bro? You know that's not how it works.
But is it using the globe? Let's check. So again, let's plug in the coordinates for the GP of the star, so minus 40.1, minus 78.3, and we want to ask it the coordinates of the point that is 3,163 kilometers away at an azimuth of 123.25. And surprise, surprise, we get 50 degrees south and 40 degrees west. So Brian, this is pretty clear that your three circles of equal altitude are only circles on a globe. They are just simply projected using the Haversine formula. You are using the globe.
Roohif, man, you're claiming I'm using a globe. So if it lines up with reality, then, and we know Earth's a globe, then he must be using a globe because it works. Bro, you sound like McToon, dude. Like the Haversine formula is restricted to the surface of your globe. But we'll go over the Haversine. But first, let me demonstrate the principle again, because I did precisely what you asked. So this time I'm going to use a North Pole egocentric position. Okay, so the observer is centered at the North Pole. So I use 6,665 kilometers for two of the circles. That's the maximum distance. That's about 60 degrees. That's about as far as navigators will claim to before the measurements start becoming unreliable. Now, the only thing that matters here is the outside circle from the center point. Okay, that's where all the circles are intersecting. You said three circles of equal altitude intersecting. I showed how they're all circles of equal altitude individually, and now they're intersecting at a fix. You challenged me for three circles of equal altitude intersecting at a fix. And that's precisely what I did, Roohif. Now I challenge you to use Google Earth and do the same thing you applied to my demonstration using the same points down by South America. I don't think it works like you think it does, man. Roohif, you're basically saying since it works, I must be using a globe. Even if I was using Haversine and applying it to a celestial sphere, since when is Haversine restricted to the surface? It's not that the flat Earth has to use a globe, it's that the globe using the Haversine has to use a flat plane. The three angle measurements have a horizontal plane in common. That's the only way it works. That's why it doesn't work from the surface of a sphere, Roohif. It's the same difference projecting onto a celestial sphere from a plane down below. There's literally no difference if I even use that method. Now, I'm not even trying to get you to pay me 10 grand, Roohif. I think you know better than that. It ain't like you don't have it. And it ain't like I didn't do what you said I couldn't do. But still, you know what I'm trying to come up with. and I'm trying to come up with enough money to put this whole debate to rest with one test, and that is measuring LIGO in 3 points. If I didn't know any better, man, I would think you're scared of the results, man. Like you're willing to renege this whole challenge, give me nothing, and send a surveyor out there to do differential leveling to measure LIGO when the results would be meaningless. Okay? Now, if LIGO is what you say it is, and I go out there and measure it, then it'll mean a million times more coming from a flat earther who measured it, if you're so certain of it. And you'll have flipped a flat earther, and I don't plan on being quiet about it. I don't think that's what I'm going to measure. I'm pretty sure what I'm going to measure. But if I'm wrong, I'm wrong. I will record the results, and I will go over this method with you because it's foolproof. It's ridiculous we haven't done this yet. We've been arguing this shit for, what, going on a decade? When this place has been standing there the whole time, we've talked about how we could figure it out tangibly without refraction and all this shit. It's been sitting there the whole time. It's driving me nuts. I can't make it there to do this measurement. So, Roohif, that's what I'm offering, and that's what I'm asking. It's not a win, it's not a loss, and it's not a draw. We can zip up for a minute. We could continue to debate this, but let's get some finality for once in this freaking discussion. It's been going on for almost a freaking decade.